Hi everyone, I've got a slightly alternate method of solving the 2 to the 4 now, so I thought I'd share it. Um, so the first thing you do, just like with any other method, is you orient the first two cells, just get one color all on the outside, and you do that the same way you would normally, or sorry, you get two colors all on the outside. So this solve, I happen to be doing white and yellow because those are just the ones that jumped out. Um, So, um, yeah, this setup is like bad, but that's where I was when I thought of it, so I figured may as well record it right away. So I've just got one with opposite sides correct, so I can do RKT on the... Oh, and see, there's only two there, so um, stack back, right. Do a gyro, and undo our gyro. And this is, well, okay, this isn't the best way to do this. Isn't how I'd usually do this, but this is how I'm doing this right now. So, yeah. So I'm just going to do a couple soons, because soon is the only corner OLL algorithm I actually know. I just small brained like that. So a soon and then a lefty soon will orient those, and then we put them back together and gyro. Boom, gyroed. So now we've got the yellow and white cells oriented. So those are out. Here's the part that's different. Now, normally what you do is you would build one cell up with, block 2, and then the other 2, and then another 2, and then the last 2. And you would build one cell, and then you would solve the other cell like a 3-dimensional 2x2. But what we're going to do here is actually a bit different. I want to solve one more color on these guys, or rather I want to put two of them. Let me show you, let me just show, not tell. So I've got red and green here, sorry, blue and green here, and I've got two blue greens there, but these two that are white are opposite each other. So if I just do these turns, they now line up, and I can pair those together like this, and then put them on the white cell. Now all I need to do is an OLL for the yellow cell, because we got a first layer skip, I guess. But that's the thing with this, is when all you care about is having opposite colors oriented, the case is just, it's become so general that there's a lot fewer cases. So now we just need to isolate each of our opposite colors to the side. So we've got kind of a checker and a line and just one. Just one is pretty simple. This is basic cuboid stuff. Just R2U, R2U prime, R2, and boom, that green is together, and boom, that yellow is together. And look, we got a permute green layer, we got a permute green-yellow skip. That's nice. It wasn't necessary, but it was nice. Now we just got to sort out these guys. So we can put one down, and then move that blue over to down there, and then insert it R2U, R2, U prime, R2, and neither of these layers is actually fully solved. We've just kind of got the side put together, but that's okay. On the blue, we have an opposite swap, and on the yellow, we have an opposite swap, yellow-blue, that is, and here we have an adjacent swap and an opposite swap. So we can combine the opposite swaps together. With the So to review, these, right? Hang on, no. Okay, no, we only have, what we actually have is two adjacent swaps here, because these colors are opposite and those colors are opposite. The pink and orange look really different in person. They look a lot better than they do on the video. So I can swap this block and this block at the same time using the cuboid T-perm algorithm, which is just R2U, R2U prime, R2 U prime D, which is actually just a Y prime rotation, R2 U prime, R2 U, R2 D prime. And as you can see, this cell is actually now permuted just fine. That white cell is solved. Over here, we've got opposite swaps. There are different ways to deal with the opposite swap. You could do an opposite swap algorithm if you know one with RKT. What I like to do is just do more of these giant T-perms. So after one T-perm, the blue is no longer oriented, but we have paired up these, we have paired up some colors, so just do that again. And one more, and that will solve it. Except we have RKT parity, because of course we do. So that's just R2, B2, R2, U, R2, B2, R2, U prime. And that's solved. There are a couple other cases, like if you have two adjacent swaps on opposite cubes, you can, let me just artificially set it up, I guess. So if you have, say, this on, if you have two adjacent swaps like this, and I know I'm ignoring our RKT, I know this is going to cause parity because, or a illegal state because of something like, actually no it shouldn't because they'll cancel out. If you've got a situation like this where you've got two swaps on one cell and two swaps on the other cell, we can actually combine those together. So all you need to do is make sure that the side that stays together pairs with the other side that stays together. So something like this, and so those two blues will swap and those two reds will swap, because we're swapping these blocks. So the algorithm, just to show you, and then roll back, undo the setup move, and I did that wrong, but if I had done it correctly, it would have worked. Anyway, that's the idea. Just wanted to share that little insight. It's a little bit harder to recognize, but I think it's fewer moves, which is better. So that's all. Bye.